The aim of the Refraction Lab was to find the index of refraction of the Perspex sphere. The index of refraction is defined as the ratio of the speed of light in a vacuum to the speed of light in the medium under consideration. In this case, the medium would be Perspex. In the Refraction Lab, we used a ray box, 12 volts, a single slit slide, and a semicircular Perspex block. So first you set up the apparatus as shown in the pictures. So basically this involves placing a piece of paper in front of the transformer box, placing a crystal on the paper, and constructing the normal, which is basically a line that is perpendicular to the medium, that is the base of the crystal. And so you get a single slide that has a single slit in it and place it inside the transformer box, and this creates a thin beam of light. And by manipulating the box and the paper, you can create different angles with the light. So the light strikes the crystal and is reflected off of it, and this creates two rays: the ray of incidence and the ray of reflection. The angle of incidence can be measured in accordance with the normal. You can do the same thing with the refractive ray and the normal to find the angle of refraction. And so once we measure the angle of incidence, that is the angle where it struck the sphere, and the angle of reflection, that is the angle at which the light was refracted, we use the laptops to record our data. Then we converted the answers to sine, that is we took the sine of each angle. Using this, we drew our graph. And now we will discuss our conclusions. If you've ever stuck a straight stick into water, you've probably noticed that the stick seems bent at the point where it entered the water. This effect is due to refraction. As light passes from one medium to another, it changes speed and bends. But this depends on the refractive index of the mediums, and the angle between the light ray and the normal to the surface separating the two mediums. When we conducted this experiment, we found that the refractive index of Perspex is 0.9159. This is slightly different from the actual value, and we will discuss this further in our conclusions. Now we will discuss our procedure and the actual conduction of the lab. In trial 1, we had an angle of incidence of 30 degrees and an angle of refraction at 23 degrees. 2. Angle of incidence 12 degrees, angle of refraction 10 degrees. 3. Angle of incidence 54 degrees, angle of refraction 35 degrees. 4. Angle of incidence 20 degrees, angle of refraction 10 degrees. 5. Angle of incidence 45 degrees, angle of refraction 22 degrees. 6. Angle of incidence 45 degrees, angle of refraction 22 degrees. 7. Angle of incidence 69 degrees, angle of refraction 38 degrees. 8. Incidence 126 degrees, refraction 64 degrees. 9. 106 degrees and 73 degrees, and 10, 137 and in this graph, sine I is graphed against sine R. Sine I is on the y-axis. You can see that the slope feature of the graph gives you the refractive index of Perspex. The value of the index of refraction that we gained from our graph was 0.916. The actual value of the refractive index of Perspex is 1.48. This leaves us with a percentage error of 38%. This isn't a small percentage error, so there were probably some mechanical errors involved in the procedure. For example, we could have measured the angle wrong, or the paper could have shifted slightly while we were taking down the rays. So it's probably attributed to human error. Snell's law is the formula used to describe the relationship between the angles of incidence and refraction. This is when you're referring to light or other waves that pass through a boundary between two different media. So the formula for Snell's law is basically sine of the angle of incidence over sine of the angle of refraction. Using Snell's law, you can compare this to our graph, which is the sine of the angle of incidence over the sine of the angle of refraction. Thus, the slope of this graph should give you n, the index of refraction, using Snell's law.